All right, what was done in the experiment? In the experiment, the viscosity of castor oil was determined using two different methods, an artisanal approach based on Stokes' law and a laboratory-based method using a Brookfield viscometer. For the first method, five marbles were dropped into a cylindrical container, specifically a 500 milliliters graduated cylinder filled with the fluid, and measuring the full time at three different temperatures, in this case, 28.33 centigrades, 23.88 centigrades, and 32.22 centigrades, in order to calculate the terminal velocity and then estimate the fluid's viscosity. For the second method, we use the Brookfield viscometer with all seven available spindles and three rotations speeds, in this case 20, 50, and 100 RPM for each of the tested temperatures. In this case, ambient 25.90 centigrades, warm 31.40 centigrades, and cold 20.8 centigrades. So the purpose of this experiment was to compare the results obtained with both methods, observe how temperature affects viscosity, and analyze the differences between an artisanal procedure and a controlled laboratory one.
What problems occur while performing the experiment? Well, we identified four main problems. The first one is the inadequate thermal control, because in the Brookfield experiment, poor thermal control occurred because we mixed castor oil at different temperatures, leading to unreliable viscosity readings. The second problem was measurement inaccuracies, because in the Stokes method there were small measurement errors. The third problem was invalid Reynolds number range, because in the Stokes method, Reynolds number exceeded the ideal limit of 1, causing an overestimation of viscosity. And the last problem was fluid contamination, because fluid contamination from repeated use in different laboratory instruments may have slightly altered the oil properties. These factors highlight the importance of strict experimental control for accurate viscosity analysis.
The large difference in errors between the Stokes methods and the Brookfield methods is mainly due to the precision and control offered by each technique. The Brookfield viscometer allows regulation of the shear rate and provides more stable readings, while the Stokes method relies on manual measurements such as fall time and spear alignment, making it more prone to error. For example, the Stokes method show a maximum error of 127.7%, whereas the lowest error in the Brookfield method was just 2.47%. Additionally, during the data collection, the temperature of the liquids varied. Some samples heated up or cooled down during handling, and although errors were made to keep them close to room temperature, these fluctuations affect the Stokes methods more significantly as small thermal variations greatly alter its result, which explains why the percentage error can even exceed 100%.
To anyone planning to replicate this experiment, I suggest a few key things. Above all, ensure precise temperature control, since viscosity changes significantly with even small variations. Also, avoid mixing fluids at different temperatures without proper homogenization. When using the Stokes method, try to minimize wall effects by using a wider cylinder. As for Brookfield's viscosimeter, it's helpful to measure viscosity at different speeds using the same spindle. This can reveal whether the fluid behaves as Newtonian or not. Finally, take your time during measurements to avoid errors, specifically when reading fall times or torque values. A calm and precise approach really makes a difference in your results.